All right, let's dig into cell potentials for half reactions. A half reaction with a strong tendency to occur is going to have a large positive half cell potential. So when we connect two half cells, the electrons are going to flow so that the half reaction with a stronger tendency will occur. So here, if we look at these two reactions, this is hydrogen, H plus going to hydrogen, and copper going to copper 2. We can see that this reaction at the anode has a more positive cell potential, and so the electrons are going to flow this way. Going the opposite way would be non-spontaneous. So how do we tell which way electrons will flow? We can look at cell potentials, and under standard conditions, the zinc has a positive cell potential. The reduction of copper has a negative cell potential. And so our electrons are going to flow from zinc to copper. Our zinc is oxidized, the potential for oxidation with the positive number, and our copper will be reduced, which is actually going to flip this reaction down here and change it to a positive reduction potential. So, standard reduction potential. We always have to measure half reactions against something else. We can't just send the electrons nowhere. So, we chemists have selected a standard half reaction is the reduction of H plus to H2 under standard conditions, and we've assigned that a potential difference of 0 volts. That's the standard hydrogen electrode, or SHE, has a potential difference of 0 volts. So then we can compare all of our other reactions to this standard hydrogen reduction. So our zinc going to zinc 2 being oxidized there has a oxidation potential of positive 0.76. You can review the notation down here. Notice the straight lines indicating phase changes there, going from H plus to H2 gas. Now, half cell potentials compare the tendency for a particular reduction half reaction to occur relative to the reduction of H plus to hydrogen gas under standard conditions. So half reactions with a stronger tendency towards reduction than the standard hydrogen electrode have a positive value for the reduction potential. Half reactions with a stronger tendency towards oxidation will have a negative value. And if you want to switch from an oxidation potential to a reduction potential, just change the sign. You're reversing the reaction, and you'll just change the sign on the potential. So table 18.1 here in your textbook is one that I would recommend having available as we work through this. It is the table of standard electrode potentials at 25 degrees Celsius. You can see here in the first part of the table, everything is positive. Then if we keep going, it's kind of a long table, so I didn't shove it all onto one page. Here is what we're measuring against, and once we go below that, it's all of our reduction potentials are negative, but if you change the sign, all of the oxidation potentials are positive. These tend to be oxidized, are more easily oxidized than the standard hydrogen electrode. They are stronger reducing agents. So like I said, table 18.1 in your textbook, or there's probably a more robust one farther back in an appendix. So how do we calculate cell potentials under standard conditions for a voltaic cell? What we can do is just take the reduction potential at the cathode, subtract the reduction potential at the anode. When you're adding values for half cells, you do not multiply the reduction potentials or the cell potentials, even if you have to multiply the half reactions to balance the equation. So this is the rare case where you do not multiply by a coefficient. Just keep the cell potentials where they are. The way I tend to do it, because it makes more sense in my head than remembering cathode minus anode, is figure out what your reduction reaction is and what your oxidation reaction is. Take the cell potential of the reduction, change the sign from reduction potential to oxidation potential for your oxidation reaction, and add them together. So I just simply reverse the reaction that's being oxidized. It will be backwards in that reduction potential table. So reverse the reaction, change the sign, then you can just add them together. So let's look at an example. Calculate the cell potential for this reaction at 25 degrees Celsius. Let's figure out, so my aluminum here is going from 0 to 3 plus, so my aluminum is being oxidized. And my reduction, my NO3, my nitrate, is being reduced to nitrous oxide, so NO3 minus NO. So those are the reactions that I am looking for in my table 18.1. So if I look for my reduction reaction in table 18.1, I can find it, and it gets me a E reduction equal to 0.96. My reaction of Al3 plus to Al gets me a reduction potential of negative 1.66, which means my oxidation potential for this one up here is positive 1.66. So my cell potential is 1.66, and these are all in volts, plus 0.96 volts gets me 2.62 volts as my overall cell potential. The other way to do it is to subtract take the cathode minus the anode. It's up to you. I always just flip it. All right, another practice one. I would recommend pausing and checking this on your own first. Calculate the cell potential for the reaction at 25 degrees Celsius. So we are looking for IO3 and I minus, both of which are going to get us some I2. So we have this one and this one. So our IO3 minus is a reactant just like this, so we're going to use our positive 1.20, but our iodine going to iodide is going to reverse it. We want the oxidation for that, so we're going to have negative 0.54. So if I take 1.20 plus negative 0.54, I'm going to get an answer of positive 0.66 volts. And you can see that's the answer there. All right, tendencies from our standard reduction potentials. A redox reaction will be spontaneous when there's a stronger tendency for the oxidizing agent to be reduced, reducing agent to be oxidized. So if we have the reaction going that's higher on the table, 18.1 there, going the direction as written, and the opposite for the oxidation, that's going to be a spontaneous reaction. So predicting the spontaneity, if we get a positive cell potential, the reaction is spontaneous. If it's negative, it's non-spontaneous. So here we have our reduction potential of our copper, and then we're going to reverse our zinc to oxidize it. You can see that will be a positive number. But if I do the opposite, if I keep the negative 0.76 and become negative 0.34, that's going to be a non-spontaneous reaction, a negative cell potential. All right, so predict if the following reaction is spontaneous under standard conditions. So we can look at table 18.1. Iron, going to iron 2, we're going to want to reverse. So we're going to do iron 2 plus 2 electrons goes to iron. That in the table is negative 0.45 volts. My manganese 2 plus 2 electrons going to manganese solid has a reduction potential of negative 2.37 volts, and the one that is as written is this one. This one's reversed, so our overall cell potential is going to be a negative number, so we will be non-spontaneous. If you just look at the table, the manganese is below the iron, so we're not going to be spontaneous as written. So practice, decide if these will be spontaneous as written or not spontaneous. So my table here is in order, you just don't have numbers associated with it. So you can pause the video and practice. The first one, the fluorine, is the top reduction reaction, and it is as written, so this one will be spontaneous. The next one down, the manganese one, is reversed, and the silver is as written. Silver is above the manganese in the table, so this one will also be spontaneous. Copper and the iodine, so we're looking at copper 2 going to copper solid, this one, and this one. So the one that's higher in the table is not as written, so this one will be non-spontaneous. And then the last example here, we have, again, copper 2 and copper and chromium. The copper one is as written, the chromium one is reversed, so this one will be spontaneous because the copper one is higher. So, yeah, this is the only one that's spontaneous in reverse. Next practice question, which of the following materials can be used to oxidize copper without oxidizing silver? So we want something that will be above the copper but below the silver. So the answer there, that gets rid of those two. And then we will want it as written. So our answer there will be C, iodine. Here's another practice. Again, pause and practice. Sketch and label a voltaic cell in which 1/2 cell has silver immersed in 1 molar silver nitrate. The other half cell has a platinum electrode immersed in 1 molar chromium nitrate and 1 molar, so this one will be chromium 2 nitrate and chromium 3 nitrate. Write the half reactions and overall reaction. Determine the cell potential under standard conditions. So if I'm drawing a cell, a voltaic cell, draw my beakers, draw my salt bridge, and then draw my voltmeter where I will be able to read my electrode. So I have 1/2 cell with silver immersed in silver nitrate, and my other one is my chromium here. So my silver is going to be as written. That will be my reduction reaction. And so my reduction reaction, typically we write it on the right-hand side. For my cathode is my reduction. And so my electrode there will be solid silver. And then I will have silver nitrate, aqueous here. So then over here, I'm going to have a platinum electrode with chromium 2 plus and chromium 3 plus in there. And then I can figure out my cell potential. So my half reaction for my silver is as written. My half reaction for my chromium is going to be backwards. So Cr2 plus goes to Cr3 plus 1 electron. We're going to have a plus 0.50 volts. And then plus 0.8 plus 0.5 is going to get me an overall potential here of 1.30 volts. I have to write my overall reaction. So then I'll have Ag plus 1 electron goes to Ag solid. So my overall reaction, let me change colors a second, is going to be Cr2 plus Ag plus goes to Cr3 plus Ag solid. And then if I wanted to write my electrodes here, it would be platinum line Cr2 plus, comma, Cr3 plus, double line Ag plus, Ag solid. So then we can look at the answer there, 1.30 volts. One more topic here, predicting whether a metal will dissolve in an acid. A metal will dissolve in an acid if the oxidation of the metal ion is easier than the reduction of the H+. And so any metal whose ion reduction reaction lies below hydrogen on the table will dissolve in acid. Now, it's important to note that almost all metals will dissolve in nitric acid because then you have the option to reduce the nitrogen rather than the hydrogen. And then one more random note here. Silver and platinum will dissolve in a mixture of nitric acid and hydrochloric acid. That's called aqua regia. And I happen to like history, so a historical note. When the Nazis invaded Denmark, several Nobel Prize winners didn't want their gold Nobel Prizes confiscated, and so they dissolved them in aqua regia, nitric acid and hydrochloric acid, and just left it on a shelf in a lab when either fleeing the Nazis, basically. And after the war came back, and the Nazis hadn't taken it. So their metals were recast from that gold that they saved by dissolving it. So there's some history for you. Okay, practice. Which of the following metals will dissolve in, this is acetic acid, and then write that reaction. So our cutoff point is here, so anything below that will dissolve. That leaves us with iron and chromium. And then for writing the reactions, it's going to be, writing our reactions, we're going to have iron solid plus HC2H3O2 goes to iron 2 And then C2H3O2 minus plus H2, and then you'd have to balance that reaction using the method we talked about. So what it ends up as is 2 iron plus 6 goes to 2 iron plus 6 C2H3O2 minus plus 3 hydrogens. Then the one for chromium, again, you're going to have to balance it. If you want to review on how to do that, you can go back a couple slides, or not slides, couple lectures, to chromium plus, again, 6, because we're transferring 3 electrons in both of these cases. So basically we ended up multiplying this one by 2 and this one by 3. Oh, there's no minus there. That was acetate instead. 2 chromium, 2 plus, 3 plus. Sorry, this is an iron 3 as well. Plus, again, 6 plus 3